Most people picture a nuclear power plant as something one bad day away from a disaster movie. Glowing green rods, alarms, a countdown to meltdown. But here's what's actually happening inside one right now, this second. It's not chaos. It's the most precisely controlled plumbing operation on the planet. 16 million uranium pellets splitting atoms. 300,000 gallons of water circulating every minute. A chain reaction being managed down to individual neutrons. And every single system exists because of a problem most people never even consider. The engineering goes deep, a lot deeper than you'd expect. Let's start where the whole thing begins, the fuel. Sitting inside the reactor core are 157 fuel assemblies, each one packed with 264 fuel rods, and each rod is stacked end to end with about 430 tiny uranium pellets. Do the math, and you get roughly 16 million individual pieces of nuclear fuel loaded into a space not much bigger than a large room. That's the engine of the entire operation. But here's what most people get wrong about nuclear fuel. It's not some glowing liquid or volatile gas waiting to blow. It's a ceramic pellet, about the size of a pencil eraser, made from enriched uranium-235. Enriched means it's been altered from naturally occurring uranium-238 to have a specific neutron count that makes the atoms unstable. Not dangerous unstable. Usefully unstable. Here's what happens. A free neutron drifting through the core bumps into one of these uranium atoms. The neutron gets absorbed, and that tips the balance inside the nucleus. The atom deforms. The strong nuclear force, the glue holding everything together, only works at extremely short distances. Once those particles stretch far enough apart, they violently repel each other. The atom splits into entirely different elements: strontium, krypton, barium, cesium. And here's the part that matters. If you weigh those fragments on an atomic scale, they weigh less than the original uranium atom. That missing mass becomes energy. Specifically, it becomes heat, enormous heat. But that's not the end. Each fission event also kicks out 2 to 3 free neutrons. Those neutrons travel through the core and hit more uranium atoms, causing more splits, releasing more neutrons. It's a cascade. Not an explosion, not a runaway chain. A controlled, probabilistic cascade happening millions of times every second. That's your power source. But raw fission without something to rein it in is a problem, not a solution. Here's the tension at the heart of every running reactor. Too many neutrons flying around and the reaction runs dangerously hot. Too few, and it dies completely. The entire job of reactor control is keeping that balance on a razor's edge, every second, without interruption. The first tool is already in the water. Reactor coolant contains boric acid. Boron is a powerful neutron absorber, so adjusting its concentration in the water slows neutrons down to the right speed for reliable fission. Too fast, and neutrons actually pass right through uranium atoms without triggering a split. The water itself acts as a moderator, but the boron gives operators a chemical dial they can tune continuously. Then there are the control rods. These are metal rods that slide down between fuel assemblies and physically absorb neutrons to dampen or kill the reaction. They come in types, and each type has a specific job. Black rods are made from a silver alloy with a stainless steel shell. Strong neutron absorbers. They handle the heavy lifting. Gray rods use more stainless steel and less silver, making them weaker absorbers, but better for fine adjustments. Think of black rods as the brake pedal, and gray rods as feathering the throttle. Then there are the shutdown rods. These don't do gradual. They're designed to be either fully raised or slammed all the way down into the core in about 2.5 seconds during an emergency. And here's the part that matters most. The rods are held up by electromagnetic latches. If power is lost, springs push the latches open, and every rod falls into the core by gravity. That's not a backup system. That's the primary design. Failure defaults to shutdown. There's even a set of axial rods that keep the three-dimensional energy distribution balanced across the entire core grid. But controlling neutrons is only half the job. You still have to move the heat. Everything happening in the core has one purpose: heating water. That's it. 16 million pellets splitting atoms, control rods balancing neutron flow, all of it exists to make water extremely hot. The reactor is essentially the most over-engineered kettle ever built. Water enters through a large pipe called the cold leg, flows down through a separate chamber outside the core, and then rises up through the forest of fuel rods. In about 1 second, that water picks up 73 degrees of heat, going from 537 degrees Fahrenheit at the bottom to 610 at the top. The flow rate is staggering, about 300,000 gallons per minute. That's half an Olympic swimming pool moving through the system every 60 seconds. But here's the problem nobody thinks about. Water at 610 degrees should be boiling violently. At normal atmospheric pressure, it would be. So how do you keep it liquid? You pressurize the entire system. There's a tank called the pressurizer connected to one of the hot water legs. At the bottom, heating elements boil a small amount of water into steam. Since water expands 1,600 times when it becomes steam, that expansion pressurizes the whole connected loop, pushing the boiling point far above the temperatures in the core. If pressure gets too high, cold water spray nozzles at the top of the tank cool the steam back down. Simple concept, critical execution. Because if core water actually boils, you've got two serious problems. Steam bubbles conduct heat poorly, meaning fuel rods lose their cooling jacket. And steam changes the water's properties as a neutron moderator, destabilizing the very reaction you're trying to control. The engineering details go even further. Flow skirts with precision holes ensure equal water distribution. Vortex suppression plates keep water from spinning at the bottom. Debris traps in each fuel assembly protect rod cladding from damage. Every transition is tuned, but the heated water still has somewhere critical to go. This is the part most people never realize. The water that touches the reactor core never leaves the building. It never reaches the turbines. It never makes your electricity directly. There are two completely separate water systems, and keeping them apart is the single most important safety boundary in the entire plant. Here's how it works. Superheated reactor water exits through pipes called hot legs and flows into two massive steam generators. Inside each one, there are over 10,000 U-shaped tubes, each about half an inch in diameter and averaging 80 feet long. The radioactive reactor water rushes through those tubes. Surrounding them is a completely different water supply, one that has never been anywhere near the core. That separate feed absorbs heat through the tube walls and boils into steam. The feeds never mix. The reactor water stays sealed inside the tubes, gives up its heat, flows back down, and returns to the core for another pass. The separation is absolute. But making steam isn't enough. It has to be clean steam. Water droplets carried into a turbine act like tiny rocks smashing into delicate blades at high speed, so the steam goes through multiple removal stages on its way up the generator. First, swirl vanes spin the flow to eject heavier water droplets outward. Then banks of zigzagged plates catch remaining moisture, letting only dry steam pass through. What exits the top is purified steam gas, ready for the turbines. The reactor water loop has its own critical hardware. 4 coolant pumps keep everything moving. In the AP1000 design, these are fully sealed units called canned pumps. Older reactors had external motors with shaft seals that leaked radioactive coolant. The canned design eliminates that entirely. Here's the reframe. People worry about radiation escaping a nuclear plant, but the entire steam generation system was engineered specifically so that radioactive water never once contacts the system that powers your home. Now that clean steam has somewhere to go. Clean, dry, non-radioactive steam leaves the containment vessel through isolation valves and enters the turbine building. This is where heat finally becomes electricity. The steam hits the high-pressure turbine first, expanding into the chamber and pushing rows of bladed wheels into a spin. But as steam does work, it cools, and cooling means moisture starts forming again. So there's a reheat stage between turbines that strips out that new moisture and warms the steam back up before it enters the low-pressure turbines. These are physically larger, designed to absorb whatever useful energy remains. All the turbines sit on a single connected shaft, and at the end of that shaft is an electric generator. One AP1000 reactor powers roughly 1 million homes. But here's what most people don't think about. The steam doesn't get used once and thrown away. Everything after the turbines exists to recycle it. Steam flows into condensers where a separate cold water supply, usually drawn from the ocean or cooled through those massive towers you've seen from the highway, runs through thousands of tubes. The spent steam passes over those cold tubes, condenses back into water droplets, and pools at the bottom. That water vapor rising from cooling towers is exactly that. Water vapor. Not smoke, not radiation, not pollution, just heat bleeding off into the atmosphere. From the condensers, the water gets cleaned in a polishing tank to strip out impurities picked up on its journey. Then it passes through a deaerator, a tank with a long vertical pipe that uses gravity to pull out dissolved air bubbles. After that, a series of heaters gradually bring the temperature back up to about 440 degrees Fahrenheit. That temperature matters because pumping cold water into a steam generator would cause thermal shock and damage the equipment. The feed water re-enters the containment vessel, meets the steam generators, and the whole cycle starts again. But what happens when the cycle breaks? This is where nuclear power earns its reputation, not because the emergencies are common, but because the engineering behind preventing them is extraordinary. 4 main systems in the plant, the reactor, pressurizer, coolant pumps, and steam generators, all carry sensors monitoring for abnormal conditions. If 2 out of 4 report a serious problem, that's enough voting power to trigger a full emergency response. No human decision required. Now take the worst-case scenario. Total loss of outside power. Backup diesel generators fail to start. Complete blackout. Here's what happens. Main electrical breakers trip automatically, cutting power to valves and devices designed to default to an open state without electricity. Within seconds, the electromagnetic latches on every control rod release. The rods fall into the core by gravity alone, killing the chain reaction. But stopping fission isn't enough. The core is still brutally hot. If that heat isn't removed, it will melt through metal components. So spring-loaded valves snap open, connecting a heat exchanger to the reactor plumbing. Hot, pressurized water naturally rushes into the colder exchanger tubes, which sit submerged in a refueling water tank. Heat radiates out. Cooled water drains back into the reactor by gravity. No pumps needed. If the system is losing coolant through a leak, pre-pressurized tanks below the reactor inject water forcefully. If losses outpace even that, the entire refueling pool, over 800,000 gallons, can gravity drain directly into the core. Meanwhile, the shield building itself becomes a cooling system. Hot air inside the containment vessel draws cold outside air through protected vents. That air flows along the vessel walls, absorbs heat, rises, and exits through the top. A massive water tank at the top of the building drains onto the vessel's surface, evaporating into the airstream to dramatically boost cooling. This system runs passively for 72 hours. 3 full days, no electricity, no human intervention, no action required. Here's why that matters. The most catastrophic nuclear disasters in history happened because older plants needed active systems to prevent meltdown. Pumps had to run, generators had to start, people had to make the right decisions under pressure. The AP1000 was designed around a completely different principle. In an emergency, doing nothing is the safest response. So right now, somewhere, 16 million pellets are splitting atoms. 300,000 gallons of water are circulating every minute. Control rods are adjusting neutron flow in 3 dimensions. 2 completely separate water loops are keeping radioactive material sealed away from the steam that spins a generator powering 1 million homes. All of it invisible. All of it running every second you leave a light on. You flipped a switch this morning powered by a chain reaction that started with a single neutron bumping into a uranium atom. If you found this interesting, subscribe for more. Next, we're going deeper.